All right. Unfortunately, today is the last day of my lecturing. All next week is going to be presentations, so I'm really looking forward to that. So, are there any questions on presentation stuff?
You said you said how long does you said half the presentation is going to be you explaining it, and then the other half is going to be us questioning it, right?
Oh no. So you guys will be presenting for around 20 minutes or so what you did in your project, and around 10 minutes after that we'll discuss as a class what we're going to do. Well, like what did we think of the presentation, what future work could be done, that kind of thing. So the way it's going to work, I already gave you guys the schedule of who's presenting. So one person on Tuesday, two on Wednesday, two on Thursday. There may be a scheduling conflict so we may have to start class maybe 3:30, but I'll let you know for sure. So other than that, everything should be straightforward. And there's nothing due in terms of the project until Friday, so don't worry about turning a presentation on Blackboard early, because I know some people are earlier than others, so I just want to make it consistent. Yeah, and one more thing, assignment 7 is the last assignment. It's due tomorrow, even though on the schedule it says the 31st of June. Think about it for a second. Right, so I meant the 1st of July, which is tomorrow. So, are there any questions about assignment 7? Okay, so assignment 6 is graded. Everything's posted about that. Assignment 7 is due tomorrow. Projects are due on the next Friday, and the final exam is out, both parts. So again, there are 200 points available, and you can get up to 120, so you get a little bit of extra credit there. And of course, if you do better on the final, then it replaces your midterm grade with whatever you get on the final. So, any other questions before we return to researchy stuff? Okay. So, last time we were talking about, we've always been talking about P versus NP, right? We want to be able to either separate these two or say that they're the same. So, recall that P means polytime computable, and NP is polytime verifiable. So P is I'm given an instance, and I am able to say yes or no for a particular problem in polynomial time in terms of the size of the input. And verifiable means that I'm given a candidate solution, and I can verify in polytime whether that is an actual certificate of that problem being in, for that instance to say yes or no. So I can verify whether a solution is correct in polytime. So I don't have to find a solution there. And of course, that's the million-dollar question. We don't know how to separate these. And so we started thinking about, well, we don't always care about time. We sometimes care about space. So we talked about some other classes about polynomial space and also lesser space. So at the end of last time, we came up with this diagram, essentially, of the hardness of problems. So in the middle, we had P and NP. So as I said last time, if I move to the right, that means more computationally hard. So we know that every polytime computable algorithm can be verified in polytime. So P is not as hard as NP. And we started thinking about other types of classes. So instead of polynomial time, we also thought about polynomial space, which we call P space. And so essentially, why do you think I put NP lesser than P space? Well, if I can solve an NP complete problem in polynomial space, then I'm already done, right? Because I can just reduce to that complete problem and then just run it in polynomial space. So the algorithm we came up with this was for the NP complete problem 3 set. So recall that for 3 set, we have a formula in 3CNF. And so essentially what we can do is we test every variable of the formula to be true, and then we see what the result of that is. If it's true, then we just verify that the formula is satisfied. Then I try true for the first n minus 1 variables and false for the last variable. But for the first assignment for all true, I throw away the result. I reuse the space. So the main advantage of having a polynomial space algorithm is that I can reuse space. But for P, I can't reuse time. Once I use time, I can't get it back. So I can just try all 2 to the n assignments to the variables, and for each one, I just erase what happened previously. I just try every single one. And I keep track of if any of them have ever said yes. So therefore, that's a polynomial space algorithm, because I only need linear amount of space to store all of the values to the variables, and then a constant amount to figure out what the value is at the end. So therefore, NP is a subset of P space. But then we started to figure out, well, what about over there below P, and what about above P space? And so we reasoned that above polynomials are exponentials. And we also note that for anything related to time and space, space is going to be at least as powerful as the time class, because we can reuse space, but we can't reuse time. So the first one for exponential must be exponential time, then exponential space. So the first one we came up with was exponential time and exponential space, which I call x time and x space. And also we can reason about doubly exponential time, then doubly exponential space, and keep going. But I'm not going to worry about those. And so some complete problems for x time, for instance, are generalized chess, and checkers, and a bunch of 2-player games like this. And so what we want to figure out is how do these classes relate to each other. And so we know that P is a subset of NP because non-determinism will be at least as powerful as determinism, but we don't know whether they're the same or not. And we also know that NP is a subset of P space because of what we just talked about, but we don't know that either. And for P space, it's a subset of X time because what we can do is we can simulate for a P-space complete problem, which I haven't said yet, but when I show you it, we can simulate it in exponential time by trying all possible assignments, which is essentially the same thing here, but I keep track of each one of them. Actually, I don't have to, but I can if I want. So P-space is a subset of exponential time, but we don't know that either. And so that should make you feel a little bit gloomy, right? That complexity theory, which is what this is called, is kind of all about these negative results here. But what we were able to know is that we know that P and X time are different. We know that P and X time are different due to something called the time hierarchy theorem, which we talked about last time. So we know that P and X time are different, but so therefore at least one of these three is a strict inclusion because these two are different, but we don't know which one, and we conjecture all three are. All right, so any questions about that? So now we're talking about this side. Now I want to talk about this side. So we have polynomial time and polynomial space. So something that's less than polynomial, we reasoned is logarithmic time and space. So those two classes are L and NL. And so, of course, when we defined reductions for NP complete problems, we used polynomial time because we don't want something that's more powerful than the class. And polynomial time seemed like a good reasoning for NP complete problems. But we can't use that for NL, right? Because if we did, then that's more powerful than the class itself, as I'll explain in a second. So what we use here are what are called logarithmic reductions, logarithmic space reductions. So among NL complete problems, I need to be able to transform one instance of a problem to another in logarithmic space, not in polynomial time. So, of course, we know L is a subset of NL, right? Because non-determinism is more powerful than the determinism one. But we also know that NL is a subset of P because of the same argument as, actually I'll get to that in a second. But it's the same argument as something over here. All right, so you may reason, well, we don't know whether P is equal to NP, but what about the P space thing? Are they the same or not? Like the NP, like a non-deterministic model of P space, called NP space. So what about that? Well, that actually turns out to be true, that they're both the same. And that is due to a theorem by Savage in 1970, which said that if you have an NP space algorithm, you can convert it to a P space algorithm. So you can actually remove the non-determinism there. And so effectively, NP space is a subset of X time, and that actually is analogous to what the reason why NL is a subset of P. Okay? So, of course, we don't know whether NL is a subset of P, and we actually don't know whether L is a subset, a strict subset of NL. So, something we actually haven't talked about, well, we talked about complete problems here, but we haven't talked about complete problems here. And so, an example of an NL complete problem is the path problem. So the path problem is given a directed graph, G, S, and T vertices, determine if S is connected to T by a path. So that's a natural question we want to figure out. And that problem turns out to be NL complete, which I talked about last time. But we also know that that P, if we invert the problem, so everywhere I said yes, now I say no, and wherever I said no before, I now say yes. So therefore, I can just invert the answer from before. And so that's a class which we call co-P. So basically what is called the complement of P. So we know those are equal, because we can just flip the answer. But since for non-determinism, we may have many computation branches happening at once. So on one branch, I may say yes, and on another one, I may say no. And so if I just invert the answer, I said yes on one pass, so therefore I must say yes. But if I flip the answer, I still say yes, because one pass still might say no. So we don't know whether NP is actually equal to co-NP or not. And that's actually a major open question, almost as important as the P and NP question. And that's actually one of the extra credit in your assignment 7. For P space, because it's deterministic, we have that is equal to co-P space, because it's deterministic. L is equal to co-L for the same reason. And we don't know whether these are equal for the non-deterministic one. We do know that they're equal for the polynomial space version, but what about the non-deterministic log space version? It actually turns out that they're equal to L, not co-L, co-M. And so it's actually quite interesting if you look at this. You have an example of whether we don't know the deterministic versus non-deterministic are equal, but the non-deterministic is equal to its complement. We have that we don't know both of them. We don't know if the deterministic is equal to the non-deterministic, and whether the non-deterministic is equal to its complement or not. And we have that they're both of the directions are true. That is, that the non-deterministic is equal to its complement, and the deterministic is equal to its non-deterministic version. So you actually get all three flavors there. All right? And for the ones we don't know, I think for every single one we believe that they're all strict. We don't know if we believe that all of them are strict and none of them are equal for the ones we don't know. Okay? So, and some other things. One more inclusion that we know that is strict. We know that P is not equal to X time. But what about the space ones? We actually do know now that L is not equal to P space. Actually, a stronger one is NL is not equal to NP space. But since Savage said that NP space is equal to P space, we know that these are different. So these are different by what is called the space hierarchy theorem, which we talked about last time. And I believe there's another one. No, that's it. And actually, no, we have that. Let me get this right. I believe that P space and X space are different for the same reason. But I'm not exactly sure about that. I believe it's true because of what the space hierarchy theorem says. Well, what the space hierarchy theorem says is that if you can solve it in f of n space, you can't solve it in little o f of n space. And what was little o f of n is strictly less than f of n, asymptotically. So exponential space is clearly more asymptotically than polynomial space. Okay. So that's where I believe I left you guys last time. So are there any questions about that?
Wait, you said P space and exponential space isn't the same because the same theorem?
Yeah, for the same reason. Yeah, because log space is clearly different than polynomial space. Yeah. So, any questions other than that? Okay. So, we've been talking a long time about completeness for NP in the hopes that we can be able to separate P and NP, right? If we can find such a complete problem and show that it's not in P, then we just separated P and NP. But what about some of the other ones here? There's clearly a lot of work here, and believe me, there's a ton of work that's been done in this area. So what we're going to do is we're going to first focus on trying to separate these two. Okay. We don't know if these are different. We don't know if these are different, but we're going to talk about evidence for why these two are different. All right? So that's what we're going to do next. So to talk, before we even get into the constructions for why we believe they are different, we need to talk about what are called oracles, which is actually one of the extra credits in Assignment 7 also. So what is called an oracle for a problem A is a device that when presented an instance of A, answers yes or no correctly in 0 time. Okay, so an example of this is like if you have an oracle for a 3 set. Obviously, this is very hypothetical, but it's what's able to help us separate these two. So let's say we have an oracle for 3 set. So this oracle will be presented a formula, a Boolean formula, and what it'll do is it'll tell me yes or no instantaneously whether that formula is satisfiable or not. So I don't know how this device or machine is built. All I'm doing is I'm presenting it an input, and it'll give me a yes or no answer in 0 time. All right. So let's think about, first of all, just as a warm-up, and we need to write these a different way. So an algorithm with, I'll just give it a name, an algorithm B with an oracle for problem A is b to the a. So the way that this is written is that I have some algorithm and it makes some calls to this oracle A. So an example of this is if I write this algorithm B with an oracle for 3 set, then I just write it like this. And in the course of B, it'll make some requests to 3 set with some formula, and then the oracle will return the answer, and then B does something with the answer. And so what has been done is, well, we don't know whether P and NP are different or not, but maybe they are with respect to oracles. Maybe if we present oracles that are powerful enough or not powerful enough, then maybe we can try to separate them there. And unfortunately, that has been tried and is actually not true. So there's a theorem that says that there are oracles, A and B, such that P to the A, so any polynomial time, anything in P with an oracle for A is equal to NP with the same oracle, and P to the B is not equal to NP to the B. And so I won't go into the one that separates these two, but for the one that is equal, an oracle that is much more powerful than NP is clearly enough to get us to have equality. Because if I have some really powerful oracle, like think of it as a reduction that's really too powerful, then I'm just really solving an NP complete problem at that point anyway. So therefore I get equality. Okay, so that's a good one. And I'm going to introduce one problem before we actually get into what is called the polynomial hierarchy. But before we get there, I mentioned that there's a p-space complete problem. And it's basically a generalization of 3 set, which we talked about last time. And so I'll just say that here. P-space complete problem. And that problem is called TQBF, which stands for totally quantified Boolean formula. And what you're given is, you're given a formula phi, just as in 3 set. You can actually make this in 3CNF as before, so that doesn't change. But what does change is how the variables are presented. So you have quantifiers on all the variables, because it's called totally quantified. So let's say that the variables are x1, x2, up to xn. Then I have some quantifier on x1, quantifier on x2, so the quantifiers may or may not be the same. And then I have, for all the variables, I have a quantifier. Where qi is either exists or for all. So we talked about last time that exists means that there is a setting to, let's just say for x1, if q1 exists. So that would mean that there is a setting to x1 to make the formula true, right? And if it were for all, then that means that for every single setting of x1, the formula must be true in that case, all right? And that problem turns out to be p-space complete in the same way, almost the same way that 3 set was complete. Okay, I think that is enough introduction. So are there any questions before we get into the last bit? Okay, so I'm gonna really work with mine right here. Hopefully not too much. So now we're gonna actually try to give some evidence for why NP is different from p-space. And so an idea of this is to try to separate these by some kind of hierarchy. So if you have some hierarchy which you know is different at every level in the hierarchy, then NP is different from p-space. Okay, so what we're going to introduce is what's called the polynomial hierarchy. And this is how it's presented. So what you start off with is P. And you call the first level level 0. And the way that's written is sigma 0P. So the P will stay constant and sigma will stay constant on one side of the hierarchy, but 0 means the 0th level of the hierarchy. At the first level, you have NP. So you define sigma 1P to be NP. And then after this point, it basically goes crazy. So the next level in the hierarchy, and every level after it, you take the previous level and you add an additional oracle on top of it. So the second level in the hierarchy is sigma 2P, obviously. And that is NP with an oracle for NP. So essentially this means you're getting an oracle for 3-set, and you're also getting a non-deterministic machine with access to that oracle. All right? And then for the next one, you get sigma 3P, and that is equal to, hold your horses, NP to the NP to the NP. So it's starting to get a little crazy, and then I bet you can guess what the next one is, and it goes on forever. All right. But we also want to make sure that we handle the Cohen side of the argument too. So there's a second side of the hierarchy, which is called, instead of sigma, is called pi. So this one is called pi 1p, and that is just co-NP. And then you have second level, again, is on this side is pi 2p is co-NP to the co-NP. Third level, I bet you can tell, is co-NP, co-NP, co-NP. And this actually does go on forever. And so you can have arbitrarily high levels of oracle hierarchies here. And so you may think, well, we don't know whether this seems different, but surely this seems a little different, right? If you're given an oracle for NP, it surely must seem like it's getting a lot more power. Like you're answering 3-sat questions in 0 time, which seems completely crazy. So it seems like a lot higher. But it turns out that, and it's one of the exercises in homework, is showing that P to the P is equal to P. So given an oracle for a P problem and polynomial time with that oracle, you still get a polynomial time algorithm. So whether these two are different is an open question. Okay? And you also have other containments in here. So these arrows mean containments. Obviously, NP to the NP is at least as powerful as NP because this doesn't even have an oracle at all for it. So you have other containments like co-NP is contained in here and the other direction. And you have this kind of cross behavior here. Okay, and it goes all the way up. And if you look on Wikipedia polynomial hierarchy, they have a nice figure that looks like this. Any questions about that? Yeah.
So P to the P equals P because the oracle for P, it returns it still has to run it in the polynomial time? That's the same as the...
You can think of it as polynomially many queries to the P oracle.
I see.
It's equivalent to say that.
Okay.
Yeah, and it's one of the questions in the homework, so I won't say why that's true, but you can actually show that.
Okay.
And it's not too difficult. So, but we don't know whether this is true. So this is actually what is called being low for yourself. Low for yourself. So P, because of this, is low for itself, but we don't know whether NP is low for itself. And some other classes, like even PSPACE, they're low for itself, but we don't know for some other ones whether they're low at all. Okay, so after that entire hierarchy, we're going to define the polynomial hierarchy to be the union of sigma kp for all k at least 1. I think that's what I defined it as. Yeah. Okay, so from every level up here and all the way up, we're going to define that as the polynomial hierarchy. And so you may want to figure out, where does pH belong on this chart? And you can actually define it as k at least 1 of the other side, because of these cross containments. But you can define it either way. All right. So the way that, this may seem unrelated, but the way TQBF is often presented is that the first quantifier is written as exists. The second one is for all, exists, for all, etc., until the last variable. So the variables of TQBF are often, they're alternating, and they start with exists. And so there's an alternate formulation of the polynomial hierarchy that says, yeah. So let's just start over here. So so how should I say it? An algorithm. A is in sigma I p. So it's in the what is called the ith level of the hierarchy. So this is first level, second level, third level. If there is a poly time algorithm B such that on input X it's basically TQBF. So you have a bunch of variables which start with exists, for all exists, in that order. So exists U1, for all U2, exists X3, up to whatever quantifiers is for I. But this should be X, this should be U. UI. So I have I alternations here, which is why it's in sigma IP. Such that M, no, not M, B on, oh, I should write this differently. So X, such that on input X for A. So the key here is that A, the input X is for A. So because B will take a lot more inputs. So B on inputs X, U1, U2, up to UI, says yes. So that's a long definition, I know. But it's essentially the same thing as the TQBF thing, but for TQBF, I can have any number of variables that I want. But here I'm fixed to I, right? So that actually shows that the polynomial hierarchy is not as powerful as p-space, because TQBF is p-space complete. So it can't be harder than p-space. On the other hand, we know that it's at least as powerful as NP, because NP already is the hierarchy. And we have parts of the hierarchy which are more powerful, possibly, than NP. So therefore, we know that the polynomial hierarchy must live in here somewhere, right? It may be equal to p-space, it may be equal to NP, we don't know for sure. Okay, so that was a big introduction to one of the basic results, which is the main reason why we believe these to be different. So we know that p-space has a complete problem TQBF. So we may want to figure out, does the polynomial hierarchy have a complete problem itself? Because if we actually are able to show that it doesn't have a complete problem, then it can't be TQBF, right? And therefore, we just showed that there's a PSPACE algorithm that's not in the Poly hierarchy. So therefore, we showed that they're not equal. But we actually don't know whether that's true or not. But what we do know is if there is a Poly hierarchy complete problem, I'm going to call it A, then the Poly hierarchy only has a finite number of distinct levels. Okay. We believe that each one of these levels is different, is strictly more powerful than the last one, but we don't know that for sure. But it turns out if you really do have a complete problem for the entire hierarchy, then you only have a finite number of levels. And we're going to go over that in a second. So, let's see. I'll do it up here. No, I'll do it here. All right, so the way we can do this is proof. If there is such a thing, then what we can do is there is some level for which everything above it is the exact same level. So suppose A exists. So suppose that there really is a complete problem. Then we know that pH is the union of all the levels. Right, that's just the definition. Well, we know that A must live somewhere in the hierarchy because it's complete for the hierarchy, right? So therefore, A is in sigma JP for some J. I'm just supposing that there is some finite J for which this is true. Because it's complete for all B in the Poly hierarchy, then B Poly reduces to A, just by the definition of reducing. Yeah, so since it's reducible to this, we know that since it reduces to here, then B can't be any harder than A. So therefore, it can't be in a level that's higher than A itself. So therefore, B is in sigma JP also. So therefore, every single problem in the Poly hierarchy, no matter which one you think, is in this finite level. So no matter if it's much higher, if it can reduce to this problem, then it can't be any higher than that problem itself. So therefore, pH has a finite number of levels. Okay. So I think I have another result. Another one is, so we believe that every single level in the hierarchy is different from each other because it seems like an oracle gives you a lot more power. Another result that we have is that, well, we don't know whether NP is equal to co-NP. So let's assume that they are. So if NP is equal to co-NP, then the Poly hierarchy collapses all the way down to NP. So it goes all the way down to the first level. And this actually works if you assume that any two adjacent elements in the hierarchy are the same. So for example, if you assume these two are the same, then everything's going to collapse down to here. And the reason why is that, well, if we look at the hierarchy itself, so we have NP over here and co-NP. So now I'm going to assume that they're the same. So if I make this equal to NP, then we look at the next level. So this is NP to NP. then if we look at this side, well, that's just NP to the co-NP. Well, co-NP is equal to NP to NP because co-NP is equal to NP. And so you get a collapsing of that, right? And actually, because that actually doesn't show that that these two levels are different. It shows that across the levels that they're the same, but we don't know vertically whether they're the same. But because of this actually, I won't prove it here. If you have a language that's equal to its complement, then you have it be low for itself. So therefore, because NP equals co-NP, then NP is equal to NP to the NP. And then by induction, this level is equal to here, then the third one is equal to the second, which is equal to the first, etc. So therefore, we actually don't think that NP is equal to co-NP or not. So that's actually evidence for why we believe it to be, for them to be different. Okay? Any questions on that? So I want to talk about one more topic, which I think is pretty interesting pretty quickly, which is actually somewhat different than what we've been talking about. So we've been talking about these NP complete problems or any completeness problems that are quite intractable in nature. So like 3-set, we know we can solve it in exponential time, but it may be interesting to figure out what about the problem is difficult, right? Because we can just say the whole problem is difficult, but like what about the problem is difficult? So what has been done is trying to analyze what about the problem is difficult, and then trying to extract that out. And so if we are able to extract that information out, then if we keep that part of the problem kind of smallish in some sense, then the problem becomes tractable. Because if we keep the hard part easy, then the whole problem becomes easier. So that's what we call parameterized complexity. So this is called parameterized complexity. And so a parameterized problem P is a set of two tuples, W and X, where W is the, well, not X. I can't read my own writing. It's W and K. It actually doesn't matter the name, but K is the one that's used most often. So W is the input. So that doesn't change at all. So it's like a problem, and you provide some input to it, or to the algorithm for that problem. But the difference here is that K is the parameter, what is called the parameter. And so actually, this is not the parameter, it's a parameter. Because you can actually specify multiple types of parameters to a problem. And so what people want to figure out is, let's try to extract all the information of the hard part of a problem into this K. Like, let's make the running time very computationally easy for W, but maybe hard for K, right? Because if we keep the value of K small, and no matter what input size we give it, then the problem becomes much more tractable. Okay, so we have two types of classes that we're going to talk about. So what are called XP, and I have no idea what that stands for. So this is the,
is it XP or KP?
I love that, yeah. It actually is XP here. So does anyone know Eric Domain? He's a famous computer science professor at MIT. And when he taught a class that involved parameterized complexity, someone asked him what XP meant, and he said experience points. I don't know. So I thought that was pretty. Yeah, I thought that was pretty funny. So XP is given L and K. So I'll call it P to make it consistent. So I'm given this problem, which will be provided inputs, and that K, which is this K here. So W will be provided to P, and K is the same here. So for any input W to P, it is solvable. So whether it says yes or no, in the size of W to the F of K time. So the only thing I haven't defined is this F. So this is unbounded. Or unlimited if you want to think of it that way. So essentially what, so F of K could be triply exponential time in terms of K, but we need to have the size, the running time be the size of W to whatever that function is. And we have, so that one is actually quite a large class and not many people use it a lot of the time, but we'll use it a little bit here. And so F of K obviously is unbounded time. But a more tractable one, which is actually used a lot, is what's called FPT. So this actually does stand for something. It stands for fixed parameter tractable. So what this is given this tuple PK for any input W to P, solvable in its W, the size of W to a constant, and I'll actually say that in a second, times F of K. So instead of having F of K, this possibly very large function, being in the size, in the exponent of W, we extracted it out and made it a multiplication thing. So, and this constant right here does not depend on K at all. Okay, so it really is a constant like 3, for example. Okay, so let's just go over an example. We actually know that one result is that P is a subset of FPT, and FPT is a subset of XP. We know that this inclusion is true because if you have a constant here times a really large function, it's much less than this input size to the really large function. So this is much larger than this potentially. So we have this inclusion, and this inclusion is true because this is effectively polynomial time right here, because it's just input size to a fixed constant, which is polynomial. But what you do for the P problem is just you ignore the parameter always, right? So if you just ignore the parameter, then this F of K just goes away. Okay? So we have P as a subset of FPT. All right. So let's talk about one problem, a concrete problem that we've been talking about. So the problem that we've been talking about are a lot of these NP-complete problems, and so let's analyze one of them. So we're going to define not vertex cover, but what is called K-vertex cover. So recall that vertex cover means that you choose a subset of the vertices such that every edge touches one of those vertices. So just as an example, if I make a cycle graph, so I want to choose a subset of these vertices such that I hit at every single one of these edges. So if I hit this vertex, if I choose that vertex, then this edge I counted and this edge I counted, right? And then now I just need to pick other vertices. So if I pick this one, then I chose that edge, I touched that edge, and then if I chose that one, then I chose those two edges too. So therefore, I have a vertex cover of size 3. And so, of course, I could choose every single vertex if I wanted to, because every single one would touch every edge. But what is interesting here is that this problem is defined as given a graph G and an integer K, and G has a vertex cover of size, I'll make it exactly K. You can make it less than or equal to K, because if I say at least K, then I could just pick every vertex if I wanted to. But the interesting case is when it's K or less. So what we can do is, we're going to show that K vertex cover is in XP, then we'll show it's in FPT. So why is it in XP? So K vertex cover is in XP. Well, I'm given this K, and I want to make sure I have the running time, the size of the graph, to some function of K. As long as I can compute the function, that's all I care about. So it's an unbounded function, essentially. What we can do is, well, if we want exactly K, what we can do is we can go through every single choice of vertices which has size K. So if it were 3 for this graph, I would choose every single triplet of vertices in the graph, right? So I would choose maybe these 3 to start with, then I would choose these 3. I would go through every single choice of 3 vertices in the graph. And then for each one, I'm going to check if any one of them is a vertex cover. Okay? So let's think about that. Well, I have the size of V vertices in the graph. And what I'm doing here is I'm going through every single possible choice of K vertices in here. So therefore, that's bounded by V to the K, right? And then now I have, for each one of those, I need to check whether it's a vertex cover or not. So what I do, I go through every single one of them, and I check every single edge connected to one of those K vertices. So we know that that's bounded by some constant, so let's just say that it's bounded by V squared, because we know there can't be more than V squared vertices in the, there are no more than V squared edges in the graph. So therefore, we can solve it in V to the K plus 2 up to a constant time. Because we can just go through every single iteration of the K vertices. Okay? So that's just a brute force approach. Okay? Any questions about that? So now we're going to make this a little bit more interesting. So this is not an FPT algorithm, because I don't have V to a constant, because K is, we need the constant up here to not be dependent on K, and we would want the function to be multiplied by the size of W here. So we don't have an FPT algorithm yet. Well, let's reason about this for a second. What we can do is, let's just say that I had the original graph back. Right? So I'm not going to assume anything about the graph itself. I'm just going to pick one vertex. Right? Oh, no. Well, I'm going to do the opposite. So, of course, for a vertex cover, I need to include every edge touching one of the vertices, right? So it doesn't matter what edge I pick. I need to pick one of them. So let's just say I pick that one. And then I'm just going to make a choice. Include one of the vertices on either end, right? Because I need to include one of them, right? So let's just say I pick that one, just arbitrarily. And then what I'm going to do is, well, if I pick that vertex, I don't need to worry about any of the other edges, right? So I can delete every single edge that's incident adjacent to this vertex. And I can actually delete the vertex itself too. Because, so now what I need to do is, or actually, I can leave it by itself if I want to. Then I'm going to repeat the procedure. I'm going to pick another one of the edges and then do the same thing. So let's think about the running time of this. Well, I have the size of E edges, right? And so there are 2 endpoints on an edge, right? Yeah, there are 2 points on an edge. So I'm going to make a choice which one I go to, right? So I have 2 choices for each edge. So 2 choices for the first, 2 choices for the second, 2 choices for the third, all the way until for all the edges. So therefore, I'm going to run this. I have 2 to the E number of edges, number of choices that I need to make. Okay, and let's think about this. For each one once we make all the choices at the very end, I need to check that essentially that there are no edges left, right? And that we have the number less than k. But for each one, we just need to check that, that for each of the edges we've actually included it. And we were able to bound this by the number of vertices squared. So the number of choices I need to make times the number of edges squared up to a constant. Did I do that right? Oh, it's not quite E here. It's actually a little better. Because I only need to include k vertices. Because at each one of these steps where I choose a vertex on the end, I can only afford k of them, right? So I need to only repeat this procedure k times. So for each one of these, I only have 2 to the k runtime. Because for each one, I'm only going to make a choice, and then after that, I'm going to only make k minus 1 more choices until the end. So therefore, I have v squared times 2 to the k running time. Well, this is the size of w, which is the input, up to a constant. Well, what is f of k here? Well, f of k is just 2 to the k. And I didn't impose anything on f itself. I just said it had to be a computable function, which means that I can actually figure out what this value is. And other than that, I'm able to show that this is an FET, right? So essentially what I'm doing here is I'm extracting the hard part of the problem, which is the k in this problem, and extracting that out to a function of k. And the easy part of the algorithm essentially is doing the verification on whether the input is correct. The result of the computation is correct. Okay. And there are also like the poly hierarchy, there's a hierarchy of between FPT and XP. We actually don't know whether FPT is equal to XP or not. I don't think we are sure about that, and I don't think we know that one either. But to separate this one, there's been a lot of work in what is called the W hierarchy and the A hierarchy, which essentially are the same thing as the poly hierarchy, but it's a little bit more complicated. And in that hierarchy, there's a lot of work done in terms of showing hardness for a certain problem, and a lot of games fit into that hierarchy too. I'd like to get into more topics, but I think your brains are pretty fried at this point. So, are there any questions about any of that? I think that's a good place to stop. So, that's all the lecture material I'm going to be presenting. So next week is going to be all of you guys. So, any questions before we break for this week? All right, I'll see you next week.
Next week it is.
It sure is.
Are you doing